this video, we're going to be talking a lot about matrices. So how about in this segment, we introduce matrices. What is a matrix? A matrix, let's call it A, is a rectangular array of numbers. Is a rectangular array of numbers. In our course, it'll be real numbers, not imaginary numbers. Matrix A is a rectangular array of numbers with a certain number of rows, say R rows, and C columns. Now generally, we name the matrices using capital letters from the beginning of the alphabet. Capital A, capital B, capital C. Later on, we'll use X and Y, but those will be what's called column vectors. But generally speaking, we use capital letters from the beginning of the alphabet. Say A can equal 3, 1, 2, 3, negative 4, the number pi. Now, we say this is a blank by blank matrix. And the blanks define the size. It's rows by columns. The first number will be the number of rows, and the next number will be the number of columns. Well, this matrix, it has one row, it has two rows. There's two rows. The number of columns will be 3, only because there's 3 columns. Column 1, column 2, column 3. General, we say that matrix A is an M by N matrix. That is, it has M rows and N columns. Of course, M and N can be equal. But if I just say in general, our matrix is M by M, that's saying that a general matrix has the same number of rows as columns, which is not true. Nobody says that M and N have to be the same. But the fact that they have different variables, it leaves the opening for them to be different. The rows and columns can be different. In fact, if M and N are the same, we call this matrix a square matrix. We'll write that up formally in a moment. Matrix has the same number of rows as columns, we call it a square matrix. If M equals N, that is, if A is an M by M matrix, of course I could have said N by N, Q by Q. If A is an n by n matrix, then we say that A is a square matrix. Why square? I guess because it fits in a square. In other words, you have 3 columns. If I don't put another digit to the right of the 2, there's column 1, column 2, column 3, row 1, row 2, row 3. We say this is a square mainly because the length and the width are the same. The rows and columns are of the same size. This is a 3 by 3 matrix. I can even say a 3 by 3 square matrix. If the rows, the number of rows, the number of columns are equal, we call it a square matrix. It's just a definition. Let us talk about the diagonal of a matrix. Unless otherwise stated, whenever we talk about the diagonal of a matrix, we mean the main diagonal. And I'll show you what the main diagonal is in a moment. First of all, before we can talk about a diagonal of a matrix, it has to be a square matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9. This here is the diagonal. Okay. 1, 3, negative 2, 4. This is a square matrix. This is their main diagonal, or the diagonal. The non-main diagonal, well, maybe not of course, but it would be that one. It would be this one. We only talk about diagonals, main diagonals or otherwise, if we have a square matrix. Okay, if we have a square matrix, we can talk about a diagonal. Now, I'm going to define some special diagonal matrices. A square, n by n matrix, whose non-diagonal entries are all zeros, is called a diagonal matrix. It's called a diagonal matrix. Non-diagonal entries. That means entries not on the diagonal, like the 4, the 7, the 8, the 9, the 6, the 3, the 2, and the 3 and the 2 again. If you're not on the diagonal, you're a non-diagonal entry. And they all have to be 0. So, 7, 0, 0, 0, 8, 0, 0, 0, 0 is a diagonal matrix. Why? Because everything off the diagonal, that is everything that I didn't circle, they're all zeros. 0, 0, 0, 0, 0, 0. It never, ever, ever in the definition, which is right here, it never, ever said what can be on the diagonal. It just says the non-diagonal entries are all zeros. Which means this matrix is a diagonal matrix. because everything off the diagonal are zeros. That is, these entries, all zeros. These entries down here, all zeros. It never said a word about what can or cannot be on the diagonal. This matrix is a diagonal matrix. This matrix is not a diagonal matrix because everything off the diagonal is not zero. That number is not a zero. This is not a diagonal matrix. Oh, and they all have to be square. All of the matrices I drew on the bottom, they were all square. Same number of rows, same number of columns. Before you can talk about the non-diagonal entries of a matrix, you have to have a diagonal matrix. That is, you have to have a square. I meant to say you have to have a square matrix. This matrix that I am drawing is not a diagonal matrix because there's no diagonal. You can say, yes, it is. Come on, there it is. No. We can only talk about a diagonal matrix if it's a square matrix. This is not a diagonal matrix. It's not a square matrix, I mean to say. It has no diagonal. That's what I mean to say. We can't even talk about the diagonal. There is no diagonal. So how can we talk about the non-diagonal entries? We don't even know what the diagonal is. Before you can talk about the diagonal of a matrix or things that are not on the diagonal of a matrix, you have to have a square matrix. You have to have a square matrix before you can talk about what's on the diagonal, what isn't on the diagonal, what's off the diagonal. Before you can say the word diagonal about a matrix, it has to be a square matrix. If you don't have a square matrix, don't let the word diagonal come out of your mouth. It will make no sense at all. People will think you don't know what you're talking about. Before you can mention the word diagonal, it better be a square matrix. The only exception is you can say that that non-square matrix does not have a diagonal. Okay, you can say, oh yeah, that matrix does not have a diagonal. And it better not be square. Okay. Let's talk about this diagonal matrix slightly different. Let's talk about the entries. Say for matrix A, we call the entries little a. Little a 1, 1. First row, first column. Little a 1, 2. First row, second column. Little a 1, 3. Second row, first column. Second row, second column. We're on the second row, the third column. Now we are on row 3, first column. Row 3, second column. Row 3, third column. Now, if you notice, this is the square matrix. When you're on the diagonal, no matter which entry you look at, the rows and the columns are the same. The rows and the columns were the same. The rows and the columns are the same. Okay? Now, if Aij is equal to 0, again, we're talking about this matrix A, okay? We're talking about a square matrix. If Aij equals 0, if I and j are not the same. Notice, when we're off the diagonal, the i's and the j's are different. Just because they're always the same on the diagonal doesn't mean they can't be the same in other positions. I mean, in theory, These could have been the same. All I'm saying is when you're on the diagonal, the row and the column is the same. That doesn't mean if you're off the diagonal, they're the same. Well, it turns out that that's never the case. That's never the case. If you're off the diagonal, they're always different. And if Aij is 0, whenever I and j are different, then A is a diagonal matrix. A is a diagonal matrix. A2, 3. I and j are different. If that's 0. And every case where the I and j are different in this matrix, if they're always different, if A1, 2 equals the same as A1, 3, which equals the same as A2, 1, which equals the same as A2, 3, which equals the same as A3, 1, which equals the same as A3, 2. Those are all the entries off the diagonal. If they all equal 0, then you have a diagonal matrix. If Aij is 0 for every time I and j are different, then matrix A is a diagonal matrix. Not with respect to diagonal matrices, but let's talk about this for a moment. If this is matrix B, and somebody asks you what is B21, what is entry B21? So you go to the second row, close to the 2, and you go to the first column. And it's 4. The second row, first column position is 4. B23 is going to be 0. Second row, third column. This is the second row, first column entry, second, there she is, third column entry. It says 0. You need to be able to, somebody asks you what's their A25 entry. You need to go to the second row, the fifth column, and read it off. If there is no second row, fifth column, you say, that entry doesn't exist. Now, I did say a couple of minutes ago, Gunnar have two definitions regarding the diagonal of a matrix. The first one was we defined a diagonal matrix. Now we're going to talk about a scalar matrix. A diagonal matrix, which we just defined, that has the same entries, on their diagonal, is called a scalar matrix. It's called a scalar matrix. So we are talking about a special case of a diagonal matrix. Let's talk about a 4 by 4. So if I have 7, 0, 0, 0, 0, I have to have a 7 again. 0, 0, 0, 0, a 7 again, 0, 0, 0, 0, 7. 2 comments, or 3 comments. It's the square matrix. Everything off the diagonal is 0. Everything off the diagonal is 0. That makes it a diagonal matrix, and every entry on the diagonal is equal to one another. There's the same entry in the diagonal, and let me say it slower. You have the same entries on the diagonal. Every diagonal entry is 7. that means it's a scalar matrix. If it's a diagonal matrix, that is, if it has the same numbers on the diagonal and zeros off it, it's a scalar matrix. Remember how I said it. If it has the same entries on the diagonal, that means it's a square matrix. If you have a square matrix, you have just this one number, the same number, in all diagonal entries and zeros elsewhere. Diagonal matrix. In fact, a scalar matrix. We can call it a scalar matrix. This matrix here, 3, 0, 0, 3, is a scalar matrix. It's a square matrix. Same number on the diagonal, zeros off the diagonal. This matrix, it's square, so I can talk about diagonals, and off the diagonal. All the entries off the diagonals are 0. So it is a diagonal entry. Oh, but look, the entries on the diagonal are all the same. So we can say the strongest statement. It is a scalar matrix. Every scalar matrix is a diagonal matrix. Again, this is a diagonal matrix because it's square and everything off the diagonal is 0. Everything off the diagonal is 0. It's a square matrix, so it's a diagonal matrix. But we can say a stronger statement. Since all the entries on the diagonal are the same, it's a scalar matrix. Nobody ever said what the same value on the diagonal can be or can't be. Nobody ever said a diagonal matrix that has the same entries on the diagonal is called a scalar matrix except when the entries on the diagonal are 0. It doesn't say that. You can't discriminate against what's on the diagonal. If they're all different, or if they're not all the same, it's a diagonal matrix if zeros are off the diagonal. If they're the same exact entries on in all diagonal positions and zeros elsewhere, we can call it a scalar matrix. So you must know these definitions. Do not fall behind on the definitions because I assure you your teacher will be talking in another language. Your teacher will 100% be talking in another language. One of the things I get upset about my students is they say, I don't understand nothing. I don't understand anything you're saying. Nothing. I ask them, define a scalar matrix. I don't know. That you don't have to understand anything to understand the definition. It's an array of numbers. Same number of rows as columns. You don't need to know any mathematics to know whether or not it's an array with the same rows and columns. I guess you have to know how to count. And you can learn what their main diagonal is. And you have to know what zeros look like. If everything off the diagonal is zeros, you are a diagonal matrix. In addition, if the entries on the diagonal all equal one another, you can say you're a scalar matrix. Okay. Two matrices of the same size, two m by n matrices, are said to be equal if they have the same exact entries. How about we say two m by n matrices, A and B, are said to be equal if they have the same exact entries. That is, the first rows are the same. Remember, each row has n entries. So A11 equals B11. First row, second entry of A equals the first row, second entry of B. All the way down to the last, row 1, the last entry, which is in column N, equals B1N. The second row, first entry of A equals the second row, first entry of B, all the way down to the second row, nth entry of A equals the second row, nth entry of B, all the way down to the last row, AM1, the mth row, first entry of A equals the mth row, first column entry of B, all the way down to the mth row, nth column of A equals to the mth row, nth column of B. All the entries are exactly the same. They have the exact same entries. If it weren't for the name, you would say, oh, you wrote down the same two matrices. They're exactly the same. Maybe you wrote one a little bit bigger looking than the other, or one you wrote neater than the other, but putting that silliness aside, they're the same matrices. 3, 1, 0, 4. This is matrix A. Matrix B. 3, 1, 0, 4. Matrix A equals B. They have the same exact entries. They have the same exact entries. Matrix C is 1, 1, 3, 7, 2, 4. And matrix D is 1, 1, 3, 7, 2, 4. They have the same exact entries. The top left positions are the same. The top right positions are the same. You want to call them the 1, 1 positions are the same, and the 1, 2s are the same. The bottom lefts are the same. The bottom right, they're both 7. The middle row on the left is a 3, and on the right, it's a 7. They have the same entries, exactly. And if you think about it, for the matrices that have the exact same entries, they have to be the same size. And how can matrix A have 2 rows and matrix B have 3 rows and say, oh, they have the same entries? Matrix 3 has entries in the 3rd row. Matrix A doesn't even have her 3rd row. So you can play games like this. Solve for the unknowns. 2, 3 plus x, 5, x plus y. You come to know that that matrix is equal to this matrix. Is equal to this matrix. 2, 5, 5, 8. Now, before you get very, very carried away, make sure that this is true. Well, yeah, the 1, 1 positions are exactly the same. The second row, first positions are the same. So, 3 plus x must be 5. 3 plus an unknown number is 5. Well, that number is not unknown anymore. It's 2. 3 plus 2 is 5. And x plus y must be 8. X plus y must be 8. But we just learned x is 2. So 2 plus that number must be 8. 2 plus 6 is 8. 2 plus 6 is 8. So y is 6. And I solve for the unknowns. There's only an x and a y. And I said what they each were. X is 2, y is 6. Now, of course, if in the beginning this said 15, you should say no, they're not equal. They're not equal. No matter what x and y are, 5 doesn't equal 15. The 2, 1 position will not be equal. I mean, if x is 11 and y is 13, does 5 equal 15? No, no. It doesn't depend upon what x and y are. 5 never equals 15. If you have $5 in your hands, in your pocket, and you go in food shopping, and when you walk into the shopping center, it says X is 22. And maybe it even has a big sign, Y is 11. Are you going to smile and say, all right, now my $5 is $15? The answer is of course not, because they're not equal. It doesn't depend on X or Y. All right, so let us get rid of that 1 in front of the 5. And now they are equal if and only if X is 2 and Y is 6. That seemed like fun. Let's try another problem like that. Again, solve for the unknowns. If possible, sometimes you can solve for the unknowns. Suppose you have 2, a plus b, a minus b, 7, and this is equal to 2, 7, and 5, 1. Okay? Well, the 1, 1 positions are the same, and the 2, 2 positions are the same. So what we have is that a plus b is 5. When you add these two, the a and b are the unknown numbers. When you add them, you get 5. And when you subtract them, you get 1. Can you think of two numbers that add up to 5, but when you subtract them, give you 1? You really should think 3 and 2. Okay, you should always think. It doesn't hurt. And if it does hurt, it just hurts a little bit. The pain will go away after a few hours. But think. 3 plus 2 is 5. 3 minus 2 is 1. If you add these, you get 2a is 6. And 2 times what is 6? 3. And a plus, so we have a. A plus b is 5. A is 3. So 3 plus b is 5. 3 plus 2 is 5. 3 plus 2 is 5. Hence, b is 2. B equals 2. If two matrices are equal, they have to have the exact same size, and the corresponding entries must be the same number. So if you're given the exact values in matrix A, no x's and y's, you're given exact entries in B, you should be able to tell just by inspection, yes, matrix A equals B, or no, matrix A does not equal B. They have different 3-2 positions. Okay. The transpose of matrix A, denoted by A with a T in the top corner. That is, that's how you denote A transpose, is obtained by interchanging the rows and the columns of matrix A. The transpose of matrix A is obtained by interchanging the rows and columns of A. The first row of A, to get the transpose of A, you take the first row of A, and you write it as the first column of A transpose. Take the second row of A, write it as the second column of A transpose, etc. If this is A, then A transpose. This first row becomes the first column. This second row becomes the second column. You don't like rows? Good for you. Don't like rows. We'll start off with columns. The first column became the first row. The second column became the second row. The third column became the third row. It doesn't matter whether you take rows and put them as columns, take rows and put them as columns, or, oops, so one please, or you take columns and put them as rows. Second column, second row. Third column, third row. If this is A, then we just wrote down the transpose of A. Just interchange the rows and the columns. The rows of A become the columns of A transpose. You go into the test and you're like, oh, I'm so nervous. I forget if the rows, to get the transpose, if the rows of A's become the columns of A transpose. Or was it the column of A's becomes the rows of A transpose? Doesn't matter. Just don't say that the rows becomes the rows or the columns becomes the columns, because then you didn't change anything. The light bulb should go off. Like, wait a minute. I started off with A, and I got back A. Okay, so that generates an interesting question. Is there a matrix whose transpose equals that matrix? Is there a matrix whose transpose equals that original matrix? Well, I hope you can see one really easily. I mean, how about the matrix? It has all the same entries. Oops. Let me make it a square matrix. It has all the same entries. Well, what will A transpose be? Well, instead of this first column, it becomes the first row. Instead of this second column, it becomes the second row. Instead of this third column, becomes the third row. And you say, oh, it equals to A. Now, I almost didn't include this last row in this example. Now, if you think about it, if A is m by n, then what should A transpose be? Remember, A has m rows and n columns. Well, A transpose is almost exactly like A. The only difference is we interchange the rows and the columns. Instead of n columns, it's going to have n rows. And instead of m rows, it's going to have m columns. that this just got switched. Now, if there's any prayer on, well, if A and A transpose are the same, now don't get caught up with transposes. A is a matrix, and A transpose is another matrix. Don't, for the moment, worry about how we got A transpose. Think B instead. You have matrix A, and you have another matrix, A transpose. Hint, it's matrix B. You have two matrices, A and B. How can they possibly be equal? And the answer is that the number of rows of the one matrix and the number of the rows of the other matrix must be equal. That's not enough, but that's necessary. If two matrices are different sizes, there's no hopes on them being equal to one another. Before you can even talk about two matrices being equal, they have to be the same size. In fact, they both have to have the same number of columns. Well, those two statements are redundant. You just need one of them. M must equal N. Oh, you mean for A and A transpose to be equal, they better be a square matrix. A better be a square matrix. It's not guaranteed, but if A is a square matrix, then you're okay. Another type of matrix that would be equal to is transpose. You have 2, 3, 4, 3, 4, 7, 1, 1, 11. That matrix is going to equal its own transpose because the first row is now going to become the first column, and the second row will become the second column, and the third row becomes the third column. And you say, whoa, look at this. That matrix is the same as A. I mean, look, please, make sure they're exactly the same. Okay, now you may say, well, how did you do that? Well, I made sure that row 1 and column 1 were the same. 2, 3, 4. And then I made sure that column 2, 3, 7, 1, and row 2 were the same. Column 3 is 4, 1, 11, and row 3 is 4, 1, 11. That guaranteed me that when I interchanged the rows and the columns, I wouldn't get anywhere. I'd get right back to where I started from. So you interchange the rows and the columns, or the columns and the rows, and you'll have the transpose. It's very, very simple, but unfortunately, it's yet another definition you have to know. Go home and learn these definitions. There's a lot of them. Your teacher is going to be talking in another language, as far as you're concerned. Okay. So, let's just finish with this type of problem. Okay, 2, 1, 3, 1, 4, 5, 2, 1, 1. And matrix B will be 3, 0, 0, 1, 2, 0, 0, 1, 3. And matrix C, we'll sneak it in here, is 2, 1, 0, say 1, 1, 0, 1, 1, 1. That's matrix C. We want to do a few calculations. Okay, we want to talk about how you add matrices. How do you add a matrix? What is A plus B? It's very, very simple. You add them component-wise. You add the 2 and the 0, sorry, the 2 and the 3 in the 1, 1 position, and you put that result in the 1, 1 position. Okay. You take their next position, 1, 2 position, you add them up. 1 plus 0, 1. 3 plus 0, 3. That's the last column in the first row. So now you go into the next row. The 2, 1 positions. You add them. 1 plus 1 is 2. The 2, 2 positions. 4 plus 2 is 6. 5 plus 0 is 5. 2 plus 0, 2. 1 plus 1, 2. 1 plus 3, 4. You may say, yeah, but you're picking such easy numbers. You need to know how to add. And to, add sign numbers and add fractions and add this and add that. Okay, that's a prereq for linear algebra. I'm just showing you the positions. You add the numbers in the same exact location, and you put that sum in the same exact location. If instead it was a minus b, well then I would do 2 minus 3. And I put negative 1 there. And I would do 1 minus 0. And I put a 1 there. And 3 minus 0 and put a 3 there. And 1 minus 1, which would be a 0, etc. If it says to add, you add the 2 components. If it says to subtract, you subtract their entries. Now, I hope it's clear that the 2 matrices have to be of the same size. Because, say, if matrix A had a 4th row, what are you going to add the 4 to? 4 plus, I don't see a number. How much is 4 plus, blank space? Like, I don't know. If you told me what that second number is, maybe I can I'll be able to add them. But if you don't tell me the number, there's no prayer in my adding them. So you're not able to add or subtract 2 matrices if they have different sizes. Okay, before you can add 2 matrices, they have to have the same size. They have to be of the same exact size. Now, there's something called scalar multiplication. Scalar multiplication. That's when you take a matrix and you multiply it by a real number. That real number is called a scalar. What happens when you multiply a matrix by a scalar? The answer is every entry in that matrix by that scalar in front. Each and every entry in the matrix gets multiplied by that scalar in front. In other words, what would 4 times c be? Well, you take 4 and you multiply it by matrix C. You multiply it by matrix C. 4 times 2 is 4. 4 times 1 is 4. 4 times 1 is still 4. And of course, 4 times 2 is not 8. 4 times 2 is not 4. It's 8. 4 times 1, all 3 ones, will be 4. 4 times the first 2 zeros are 0. And 4 times 1 is 4. Multiply each entry by 4. And put that new number in the original location. If you're multiplying the number in front by this 1, you better put your answer in the same location, namely the 2, 2 position. Okay, so multiplying by scalars is not a big deal, but once again, it's another thing you have to know. Okay, they're piling up. What is scalar multiplication? My teacher talks about adding matrices, scalar multiplication of matrices, when are two matrices equal, what is a transpose, what is a diagonal, what's a scalar matrix, what's a diagonal matrix. Yeah. I mean, I'll be honest, my linear algebra teacher, he made me dizzy. But then I realized that this was hardball, and I kept up with the work. You can't fall behind in this course. It doesn't work. This row down here doesn't exist in matrix A. Okay? This is hardball, absolutely. Okay, before you can add two matrices or two numbers, you have to know what you're adding. First, we have to know what A transpose is. So, I take the first row, 2, 1, 3, and I write it as a column, first column. I take the second row, 1, 4, 5, second column. The third row is 2, 1, 1. I write it as the third column. Plus 2 times B. So I multiply every entry in B by 2. 2 times 3, 2 times 0, 2 times 0, 2 times the second row, 2 times 1, 2 times 2, 2 times 0, 2 times the third row, 0, 2, 6. And now, we know what matrices we're adding. It's this matrix plus that matrix. We know what A transpose is now. We know what 2B is now. So we add them. 2 plus 6, 1 plus 0 is 1. 2 plus 0 is 0. 1 plus 2 is 3. 4 plus 4 is 8, etc. If I make a silly arithmetic mistake, it doesn't matter. It's the concepts that are important. 3 plus 0 is 3. 5 plus 2 is 7. 1 plus 6 is 7. Okay, my linear algebra teacher, he did a perfect job. He was flawless. He's an excellent linear algebra teacher, but he couldn't add two matrices. Forget about multiplying two matrices. You'd always make silly arithmetic errors, but that didn't mean a thing. It didn't mean a thing. It meant that his answers say never match the answer in the back of the book. And when I say never, I mean never. But he was still an excellent instructor. Don't worry that you make silly arithmetic errors. So linear algebra class, not arithmetic. Okay, what I'm getting at is, yeah, fine, you stink at arithmetic. And I'm going to get yelled at for this when my professor stunk at arithmetic. But this is linear algebra, and he understood that quite well. He was the expert. Okay. Let me see something for a moment. Okay. So let's get rid of this. But we'll keep the same A, B's, and C's up there, and we'll try this again. What if you wanted to do B transpose minus 2 times A? Well, B transpose. The first row of B is 3, 0, 0. So I write it as the first column. The second row is 1, 2, 0. I wrote it as the second column. The third row of B is 0, 1, 3. Since I'm writing the transpose, I'll write it as the third column. Minus, that's B transpose, this, minus twice A. That means every entry of A gets multiplied by 2. The first row is 2, 1, 3. 2 times 2, 2 times 1, 2 times 3. The second row is 1, 4, 5. 2 times 1, 2 times 4, 2 times 5. The third row is 2, 1, 1. 2 times 2 is 4. 2 times 1 is 2. 2 times 1 is still 2. And now we can do the subtraction. 3 minus 4, negative 1. 1 minus 2, negative 1. 0 minus 6, negative 6, etc. 0 take away 2, 2 take away 8, 1 take away 10, 0 take away 4, 0 take away 2, and finally 3 take away 2, which is 1. So, B transpose minus 2A equals this over here, equals that matrix. Now, instead of this problem, I modify it a little bit. I don't just want B transpose minus 2A. I want B transpose minus 2A transpose. So whatever B transpose minus is, which inside those, I want to transpose it. Well, I found out what B transpose minus 2A is. It's this. And I transpose it. That is, let's deal with columns. This first column is the first row. This second column becomes the second row of the transpose. The third column becomes the third row. And there it is. There it is. Okay? Now, this finishes the lecture, and we're going to do it for this section, but we still have these theoretical exercises to work on. 2 or 3 of them. Some teachers will want you to do proofs, and I think that's mandatory. Others, they won't. And if you don't need to know how to do the proofs and you don't want to, you can go to the next section. Want to prove that the sum of 2 diagonal matrices is a diagonal matrix. If you add 2 matrices that are diagonal, you'll get one that's diagonal. Well, diagonal means when you're off the diagonal, it's going to be 0. If you're off the diagonal, you're going to be 0. Well, if you add 2 such matrices, they have to be the same size. But if you add 2 such matrices, well then, yeah, what's off the diagonal will be 0, because 0 plus 0 is 0. 7, 0, 0, 0, 2, 0, 0, 0, 4. That's the diagonal matrix. Everything off the diagonal is 0. You add or even subtract another matrix like this. Okay? I don't really care what happens to the sum on the diagonal. But you know what? When you add those 2 entries, you'll get 0. When you add those 2 entries, you'll get 0, or subtract them. When you add those 2 entries, you get 0. When you add those 2 zeros, you get 0. You add those 2 zeros, you get 0. You add these 2, you get 0. All that is left over are the diagonal entries. And I don't care what they are. It's a diagonal matrix if what's off the diagonal is 0. It turns out that 7 plus 3 is 10, and that 2 plus 7 is 9, and 4 plus 4 is 8. Now, please don't think I just proved it. I proved when you add those two exact diagonal matrices, when you add this diagonal matrix to this one, yes, you get back a diagonal matrix. But that doesn't mean that I can't write down two other diagonal matrices and get a diagonal matrix. I can multiply numbers by 4 and always get multiples of 6. Does that mean every time I multiply a number by 4, it's a multiple of 6? No. I just set you up. I keep giving you 4 times 3, 4 times 6, 4 times 9, 4 times 21, 4 times, 72. 6 goes into all of these numbers. But 6 doesn't go into 4 times any old number. 4 times 2 is 8. 6 doesn't go into 8 evenly. So we need to prove this rigorously. A is equal to, called in brackets, little ij. And what we know is when I is not j, I know what aij is. It's 0. That's the definition of diagonal matrix. So I didn't write it down, but the theorem is to prove that the sum of two diagonal matrices is a diagonal matrix. I ran out of room. DM is diagonal matrix. Now, if I don't, I don't always know what aij is, but I know what A23 is. Okay, so now the proof. Let me write the proof up just a little bit cleaner. Suppose A and B are two m by n diagonal matrices. And then we'll do just what I was doing. Suppose A and B are two diagonal matrices of size m by m. In fact, I don't even have to say that. It's understood if A and B are two diagonal matrices, then they're square. Okay, so A, which is denoted by aij in brackets, it's just silly notation in my opinion. Sometimes I know what aij is. It's 0 if I is not j. And I don't know what it is if I is j. But because I don't know what matrix A looks like. I don't know what matrix A looks like. Other than that it's diagonal. It's a diagonal matrix. That is, if I and j are not equal to one another, it's 0. When I is j, when I'm on the diagonal, I have no idea the entries of A on the diagonal. No idea at all. Matrix B, which we denote by little bij, same story. If I is not j, I know what bij is. It's 0. But if I is j, I don't know what I get. It's just bij. That's the best I can say. Okay. Now, suppose we let C equal A plus B. Well then, Cij is going to be Aij plus Bij. To get the ij entry of C, you take the ij entry of A and add the ij entry of B to it. Well, if I is not j, this is 0 and that's 0. And it clearly tells me to add them. And if I is j, well then, I get aij plus bij. aij plus bij. That is, I get whatever. I don't care what this is when I is j. But 0 plus 0 is 0. And that I do care about. When I is not j, I'm supposed to get 0. And I did. Cij is 0 when I equals j. So, by definition of diagonal matrix, these A plus B is a diagonal matrix. Because when I and j are not equal to one another, I get 0. And I should mention that it's a square matrix. Now, if you wanted to do the difference, here it is. 0 minus 0 is 0. Instead of plus, you should have minus. Instead of plus, you should have minus. C minus B is also a diagonal matrix. Okay. Let's do scalar matrices. If you add or subtract two scalar matrices, the result will be a scalar matrix. Think about it. When you add those numbers off the diagonal, it's going to be 0 plus 0, which is 0. When you add the numbers on the diagonal, they're always going to be the same two numbers. If the first diagonals all have 2's and of the first matrix, and the second matrix, the diagonals are all 5's, when you add them, the diagonals will always be 2 plus 5. Okay, see that. 2, 0, 0, 2 plus 5, 0, 0, 5. These are the entries off the diagonals. When you add them, they'll still be 0. And on the diagonals, 2 plus 5, 2 plus 5. Yep, it's a scalar matrix. So prove or theorem or show that the sum difference of two scalar matrices is a scalar matrix. If you add two scalar matrices, the result will be scalar. And the proof is 100%, like many, many proofs in mathematics. It's 100% by definition. And I started to get much, much better in proofs when I realized that. Oh, just go by the definition. And when I couldn't do a proof, I tried to understand the definitions even deeper, even better. And finally, the proofs came out. Okay, so proof. So you should start off with two scalar matrices. Let A and B be M by M scalar matrices. Okay, so matrix A, which we'll denote by Aij in brackets, well, most times we get 0. In fact, when I and j are different, we get 0. Now, when I and j are the same, we get the same answer. Call it R. Suppose all the entries on the diagonal is R. Now, matrix B is going to be defined very much the same. we're going to get 0 if you're off the diagonal. The Bij entry will be 0. Now, if you're on the diagonal, you're going to get the same answer. But it doesn't have to be the same answer as matrix A. I mean, here, I had 2's on the diagonal, and in the next matrix, I had a different number. Okay, so call them R and S. Matrix B has letter S on the diagonal. Okay. Now, let C equal A plus B. Well then, Cij is going to be Aij plus Bij. The Cij entry will be Aij plus Bij. But here's where it comes together. If I is not j, this is 0 and that's 0. And you add them. And if I is j, well then that's r plus, and that's s. Oh, you mean r plus s? Absolutely. And then one very, very simple arithmetic to do. 0 plus 0 is 0. Oh, you mean when I is not j, that is when you're off the diagonal, you get 0. And when I is j, that is when you're on the diagonal, you always get that same answer? Oh. So, by definition of scalar matrices, A plus B is a scalar matrix. Now, what if it were subtraction instead? What if it was A minus B? What if it was A minus B? Then you would do Aij minus Bij. And you'd have R minus S, which is R minus S. Here, the magic of zeros. 0 minus 0 is still 0. So by definition of scalar matrices, A minus B is a scalar matrix. Okay, it's not that bad. We're going to try one more. We're going to talk about upper triangular matrices. A matrix is upper triangular if it's a square matrix and what's below the diagonal is 0. If everything below the diagonal is 0, you are an upper triangular matrix. Again, you have to be square, and everything below the diagonal is 0. That is upper triangular. A square matrix with entries below the diagonals, the diagonal, a square matrix with entries, let me say it here, of zeros below the diagonal is called an upper triangular matrix. Called an upper triangular matrix. Okay. Now, let's just note something. You have A11, A12, A13, 21, 22, 23, 31, 32, 33. This statement is going to be true for any square matrix. That's the diagonal and above. What's below the diagonal has to be 0. 2, 1. 3, 1. 3, 2. Notice the I entry is always bigger than the J entry. Now, I want to show that if I add two of these matrices, I'll get an upper triangular matrix. Okay, so that's the theorem. The sum and difference of two upper triangular matrices is upper triangular. Okay, so theorem. The sum or difference of two upper triangular matrices is upper triangular. If you add two of these type of matrices, you get the same one. You can say that they're closed. Okay, proof. Let A and B be two upper triangular matrices of size m by m. Need to say they're the same size, else I can't add them. Okay, so now A, which is Aij, a lot of times we're just going to get Aij, and a lot of other times we're going to get 0. If I is bigger than j, we get 0. If I is not bigger than j, now you can write it, you can write I is not bigger than j that way, or you can say I is less than or equal to j. I prefer that way. Okay, so matrix B, no reason why it should be much different. You're going to get Bij if I is not bigger than j. You're going to get 0 if I is bigger than j. If I is bigger than j. So now we add them. Let C equal A plus B. So the Cij element is going to be the Aij element plus the Bij element. But this is piecewise. If I is bigger than j, you get 0 plus 0, and to save a line, I'm going to say that's 0. And if I is not bigger than j, you're going to get Aij plus Bij. You're going to get Aij plus Bij when I is less than or equal to j. Aij plus Bij. But then we can say, then by definition of upper triangular matrices, A plus B is a upper triangular matrix. Now, if you are lower triangular, that means everything above the diagonal is 0. Notice the j's are all bigger than the i's. Up here, you have I is less than j. So if you are lower triangular, if you have two lower triangular matrices of the same size, their sum will be lower triangular. Can you think of a matrix that is both upper triangular and lower triangular? The answer is yes, you can. Go for it.